also thank you for the invitation to speak here. So I will explain in part the image and homotopy theory of what Con was talking about in the before the lunch break. So let me first say something about K-theory. So yeah, so if X is a scheme, then Grothendieck defined this group, which is the free abelian group generated by the set of vector bundles on X, and then modulo the relation that if there's a short exact sequence, this relation is imposed. So this is the most important K group. And Quillen found a way to extend this to define a spectrum or to define higher K groups. So Quillen defines a K-theory spectrum. And so it's a sequence of pointed spaces, K of xn, and together with maps from the mth space mesh, the n sphere to the m plus n space. And here symmetric means that you can have the symmetric group in letters acting on the mth space, and this makes it possible to define this strictly associative smash product. And then by definition, the higher K groups are the homotopy groups of this spectrum. So it's maps in the homotopy category of symmetric spectra from the Q sphere to the K-theory spectrum. Let's see. Now this doesn't work anymore. Okay, so K-theory knows about special values of zeta function. So for example, if K is a totally real number field, then this value of the Dedekind zeta function is given by the K groups like this. So this is a very non-trivial result, and yeah. But K-theory does not know about the whole zeta function. So for that, you need to have something with an operator on it, and an operator that has non-integer eigenvalues. So on K-theory, perhaps you have the Adams operators, but they act up to filtration with integer eigenvalues, so it cannot give you the whole zeta function. Yeah, so I will talk about this big de Rham Witt complex, but it's in some respects is similar to Milnor K-theory, so I will first explain Milnor K-theory. So if X is spec of a field, then the algebraic structure of K-theory is that it's a graded ring. It's a graded anti-commutative ring. And there's a map from the group of units in the field to K1 such that if we multiply the image of two units whose sum is 1, then that element in K2 is 0. So this is the Steinberg relation. And Milnor defined these groups called Milnor K-theory, and that's just a universal example of this algebraic structure. So whenever we have a graded ring together with a map from the units in the field to that, such that the Steinberg relation is satisfied, there's a unique map from Milnor K-theory to that ring. It's easy enough to say what that is. It's just take the tensor algebra on the units in the field and divide out the ideal generated by all tensors x tensor y such that x plus y is 1. That does not make it easy to calculate, though. So it can be quite difficult to understand the structure of this. So yeah. So now I will talk about the cyclotomic trace map, and so this is a topological refinement of the Turing character to negative cyclic homology, and yeah, so this was introduced by Bøksted, Chang, and Madsen, and I will explain what this is. So here the target is a pro-abelian group. So it's a system of groups, one for every non-negative integer, one for every positive integer r, and the system is ordered under division. And this begins as with K-theory, that one defines a spectrum, which I have called TH here, but also it's also called CHH of X, and so Kohn explained to some extent the definition of this before. And then there's this fantastic thing about this which was discovered by Kohn, that the ordinary Hochschild complex is not just a simplicial abelian group; it has this extra cyclic structure, and that gives rise to an action of the circle when you form the geometric realization. So this spectrum here comes equipped with a continuous action of the circle. So the natural thing to consider is not homotopic groups, but equivariant homotopic groups. And these are also maps in the homotopic category from this smash product to TH of X. So why is this the appropriate thing to consider? Well, in ordinary homotopy theory, every weak homotopy type can be obtained by gluing cells, so gluing disks onto each other. In equivariant homotopy theory, every equivariant homotopy type is built out of cells that look like this, so a disk with trivial action and then cross such a canonical orbit. And so if we take this cell modulo its boundary, that can be written like this. It's this Q sphere smash this canonical orbit with a disjoint base point added. No. Yeah, G is the circle group, so that's not discrete. But I will not consider. Yeah. So, but I will only consider a finite H. And so here I have written CR for the cyclic group of order R inside the circle. So this is the definition of the group in level R and degree Q in this pro-abelian group. Now, if R is equal to S times T, then the cyclic group of order T is a subgroup of the group of order R. So therefore, there's a canonical projection from T modulo the smaller group to the circle modulo the bigger group. And this induces a map in the opposite direction on equivariant homotopy groups, because this was maps out of these things. And this map we call the S-Frobenius map. Yeah. Yeah, but you can also say that each of these quotient again is a circle, and this is a degree S map from the circle to itself. Yeah. So spectra are a weakening of abelian groups, if you want, more complexes. So in homotopy theory, there's also a map, a transfer map going in the opposite direction, and this map we call the S-Verschiebung map. These are not the maps that make up the structure maps in the Pro system, though. Yes. Well, if it's, yeah. I think I only know it as being well defined up to homotopy. Yeah. So there's also a map like this, which basically is the action of the circle. And this induces a map that does not change the level, but it raises the degree by 1. And this is a topological manifestation of Con's operator, which I will call lowercase d. So it's Con's capital B operator. But then there's also this other map called the restriction map. And this is more difficult to define, but it comes from as Con pointed out in his lecture. It comes from this fact that if you smash a spectrum with itself and take the fixed set, then there's a map from this back to X, which is something you don't have if you have the tensor product here. And this is where this is basically where this map comes from, and it's this map which is the structure map in this pro-abelian group. So the maps, the Frobenius and Verschiebung maps, both commute with this map. So they are both maps of the of. That's right, R is ST. Yeah. Yeah. This uses what we call a cyclotomic structure on CHH, but which is basically this. So using these restriction maps, you can exhibit this group, or rather that homotopy type, as a successive extension of such Borel quotients of finite cyclic groups acting on CHH. And it's so similarly we can define Con's cyclic homology to be the Borel quotient of the full circle acting on Hausdorff homology. So, so when the base is the sphere spectrum instead of the integers, we get this finer structure where instead of taking the homotopy, this Borel quotient for the full action all at once, there's this way of stringing together all the finite Borel quotients in this tower. I should also say that that the fact that that these TR groups are these successive extensions goes back to work of Tom Dieck and Siegel at the very beginning of equivariant homotopy theory. Okay, so now I have explained what this target of the cyclotomic trace map is. And it has these Frobenius operators on it, and the trace map from K-theory lands in the subgroup that is fixed by all the Frobeni. So all the Frobenius operators act as the identity on the image of the trace map. This is a strong invariant of K-theory, and it can, in some cases, be used to understand K-theory. I should also say that this is, in many respects, a non-Archimedean analog of Kahn's cyclic homology. Yeah, it's not good for rational. Yeah, not good for rational. Let me also say, but these Frobenius operators do not act with integer eigenvalues. So in fact, if you have a scheme which is smooth and proper over a finite field, then the action of the Frobenius operators on this pro-abelian group, together with the Hodge filtration, completely determines the zeta function. So well, you will see when I get to the Rham Witt complex, the Hodge-Witt cohomology groups assemble in one way to give the TR groups, and then assemble in a different way to give crystalline cohomology. But both can be used to express, to give a cohomological interpretation. Yeah. Or considered as a pro-abelian group. Yeah. Okay, so now I will talk about the analog of Milnor K-theory for this theory. So we have this pro-abelian group. Now I will only consider the case where X is affine. And it has a rich algebraic structure. So it's also a anti-commutative graded ring. It has an operator D, Kahn's operator, which is almost a differential. And it has the Frobenius and the Verschiebung. As Kahn said in his lecture, pi naught is identified with the ring of big Witt vectors, which I will talk about later. And the big Rham Witt complex, by definition, is the universal example of this algebraic structure. So it is related to this TR theory in the same way as Milnor K-theory is related to algebraic K-theory. And if K is a field, then there's a commutative diagram like this. So here on the right, I have written the cyclotomic trace map from K-theory to TR. And the horizontal maps are these unique maps from the universal example of the respective algebraic structures. And I will explain later what this map on the right-hand side, left-hand side does. Yeah. Let me also give an example to say that this can be used to calculate K-theory. So this is a theorem of myself and Ib Madsen. So if A is an irregular FP algebra, then the K groups of a truncated polynomial algebra with coefficients in A relative to the ideal X. So these K groups contain the K groups of A as a direct summons, and so this is the remaining part. And these K groups sit in a long exact sequence where the other terms are made out of these big Rham Witt groups that I will now proceed to introduce. I will talk. Yeah. So now there's an intermezzo where I will define big Witt vectors and lambda rings. So so Denninger already talked about Witt vectors in his talk yesterday, and this well, so yeah. So there's this map called the ghost map. So the domain of that is this big Witt ring, and as a set, it's just sequences of elements in A. So the target and so the domain and target of this map is the same set. It's both the set of sequences indexed by positive integers in A. And that's why it's called vectors. It's these infinite vectors in A. And here's what the map does. It sends a sequence AN to a sequence WN, where the nth term is the sum over all divisors E in N, E times AE to the N over E. So the sequences on this side are called the bit coordinates of the vector, and the W's that correspond to that are called the ghost components of the vector. If A is flat over the integers, or if it's torsion-free as an abelian group, then this map is injective. And so in that case, the ghost coordinates determine the bit coordinates, but in general, that's not the case. Yeah. So what about the ring structure? So the target of the ghost map is given the coordinate-wise addition and multiplication. So it's just multiply and add sequences term-wise. And the identity element is just a sequence that has all ones. And now it turns out that there's a unique ring structure on the domain, such that this map is a natural transformation of functors from rings to rings. So that's the definition of the big Witt ring. There's a map called the nth Frobenius, which is given like this. It's a natural transformation from this functor to itself, such that if I first use the nth Frobenius and then take the eth ghost component, I get the nth ghost component. And again, asking that this be a natural transformation of functors from commutative rings characterizes this uniquely. So there's a unique such ring homomorphism. Yeah. For example, if A is an FP algebra and N is P, then this is just induced by the Frobenius on A, but this exists for any commutative ring A. Similarly, there's this map called the universal lambda operation. It's also a ring homomorphism from the Witt vectors of A to the Witt vectors of the Witt vectors of A. And it's characterized like this, that if we go with this map delta and take the nth ghost component, then that composite is the nth Frobenius that I defined before. And yeah, so this is the universal lambda operation. Yeah. And so now by definition, a lambda ring is a co-algebra over that co-monad. So it's a pair of a ring A and a ring homomorphism to the ring of big Witt vectors, such that it's a co-algebra, meaning that if I compose this with the first Witt component, I get the ghost component, I get the identity map of A, and such that this formula holds. If I compose lambda with the map induced by lambda, I get the same as if I compose lambda with the map delta. Now, if we have a lambda ring, then we can compose the structure map lambda with the nth ghost component, both of which are ring homomorphisms. So this composite is also a ring homomorphism, and that is called the associated nth Adams operator. These Adams operators satisfy that they give an action by n cross through ring homomorphisms, and moreover, that the pth Adams operator is congruent to, well, so the pth Adams operator is a lift of the pth Frobenius. If the ring A is flat over Z, so if it's torsion free, then Clarence-Wilkerson has proved that if you have this data, there exists a unique lambda ring structure that gives rise to it. So for example, if we have the monoid ring over a commutative monoid, then we can define psi n to be the map induced by racing to the nth power in the monoid. And by Fermat's small theorem, it satisfies these three properties. So the monoid ring of any abelian monoid is a lambda ring. Yeah, every lambda ring is special. Yeah. So yeah, that's yes, yeah. So if we have a lambda ring, we can forget the lambda ring structure and just get a ring. And this functor has a left adjoint, which to a ring associates the big Witt vector. Right adjoint, yeah. Which associates it's right, yeah. That's right, yeah. So so it associates the ring of big Witt vectors together with the universal lambda operation. There also is a left adjoint, and that associates the free lambda ring generated by the ring. And so Jim Borger has suggested that we should interpret the lambda ring structure on a commutative ring as descent data to some deeper base. And so for the purpose of this talk, I will call that F1. But yeah. And well, then we should think of this previous picture like this. So we should think of the forgetful functor that forgets the descent data as extending scalars up from this deeper base to the integers. And we should think of the big Witt vector construction as being the forgetful functor that forgets that the ring is defined over Z and only remembers the underlying F1 algebra. And the free lambda ring we should think of as B restriction. So, well, this begs the question of what are modules and derivations for lambda rings. And so I asked myself this question, and so yeah, it should say Beck on this. So Beck in his thesis, I think, so whenever you have a category with finite limits and an object in that category, Beck has a definition of a category of modules over X and derivations of X to an X module. So here it is. The category of modules over X is take the category over X, so the objects over X, and take the category of abelian group objects in that category. So that's the category of modules. If C was the category of rings and X was if C was the category of commutative rings and X a ring, then this category is equivalent to the usual ring of the usual category of modules, yeah. And Beck also defines derivations. So a derivation from x to an x module. So now remember, an x module is an object over x together with a plus, a 0, and a minus in this category of objects over x, to be just the set of maps in the category over x from the identity x over x to y over x. So here we didn't use the abelian group structure to define this set, but they give that set an abelian group structure. So this set of derivations is now an abelian group. And if you do this, again, with commutative rings, you get the usual notion of a derivation. So, but now if we take C to be lambda rings, then this becomes the following. So a module over a lambda ring is a pair of a module M over the ring A, and a collection of additive maps, one for every positive integer, from M to itself, such that the following holds. These maps, this collection of maps, is an action of n cross through additive maps, but they are not A module homomorphisms. Instead, if I multiply by A and then use lambda mn, I have to multiply by the nth Adams operator applied to A on the outside. Yeah. Yeah, they are psi A, psi n. No. Yeah. Yeah. So, well, let me go back. So a module was a module over the ring together with additional structure. What? No. It is exactly this. A derivation is a derivation, not with extra structure, but with an extra property. And the property is that the following holds. So that if I take A in A and use the derivation, then now I get an element of M. And if I apply lambda mn to that, I should get this. Here, this is not the eth lambda operation that you might be used to. This is the eth Witt component of the Witt vector lambda A. So these maps are not additive at all, but the sum is. So that's a derivation. And there's a universal derivation which you prove as, in the usual way. And then there's this proposition. So I was very surprised when I figured this out, because I thought maybe that derivations in the world of lambda rings should be the Rham-Witt complex, but it's not. The underlying A module of the universal derivation in the category of lambda rings is just the usual universal derivation. What? Yeah, yeah. So in other words, if A is a lambda ring, the module of Kähler differentials has this additional structure. But if we accept Borger's philosophy, then actually this should be expected. So on this side here, we should interpret this as being, So we take the F1 algebra and extend scalars up to C, and they then take differentials relative to C. And on this side here, we take differentials relative to F1 and then tensor up to C. So if this was rings, this would hold. And so you just repeat the proof in an appropriate way, and then it works in this case too. So now what about the universal lambda ring? So if I have any commutative ring, its big Witt ring is a lambda ring. And as Cartier said, this means that on its module of Kähler differentials, there's the structure of a lambda ring module. And what this amounts to is that, well, what are the Adams operators on the universal lambda ring? They are by definition the Frobenius maps. So this means that for every integer, for every positive integer n, there's an Fn linear map Fn like this. And it satisfies this formula because that's what a lambda derivation had to satisfy. So you could say, well, I could just take this as the definition, and you would be right, you could, but but try to prove that this is an additive map, for example. So the ingredients is on this side is not additive, but somehow the sum turns out to be. Yeah. 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 Yeah, and also I don't have to go to Rham Witt. It's true already on this operator exists on the level of Kähler differentials, because now an easy consequence of this is that this is a divided Frobenius. So if I first use the Frobenius on Witt vectors and then take D, that's the same as using this new Frobenius operator on dA and multiplying by n. Yeah, so I was very surprised by this because I thought that that was what the Rham Witt complex was about, that you had to go to this quotient to have the divided Frobenius operators defined. But no, they already exist on Kähler differentials. And then there's these other formulas here, which says how what happens in the case of a Teichmüller representative and how the Pth divided Frobenius acts. Yeah, this is the Teichmüller element. Yeah. Okay, so now the ring of, so now I will define, so now I have defined derivations, and now I will define the Rham complex. But there's a little twist. So the units in this ring of bit vectors of Z, there are 4 of them, and they are all square roots of 1. And so, you know, if you have any commutative ring A, and if you have a square root of 1 in it, then multiplication by that gives an isomorphism to a new commutative ring that has the same underlying additive. It has the same addition, so it's the same set, it's the same additive group. But now multiplication here is instead that A times B is UAB. And so in that ring, so over here, if 1 is the identity here, U becomes the identity here. So, so in this ring, we have these 4 units. However, everybody agrees what the identity element in the Witt ring is, namely, it's the Teichmüller of 1. So everybody agrees that this is the identity element here. But as Stinninger also explained in his talk yesterday, this ring is, the underlying additive group is isomorphic to power series with constant term 1. Yeah. And addition there corresponds to multiplication of power series. But now the question is, which power series is the multiplicative identity? And so you have these 4 choices. So you can take t plus or minus 1 plus or minus t to the plus or minus 1. So there's these 4 choices. And 3 of them appear in the literature and are called the universal lambda ring. So if people talk about the universal lambda ring based on power series, you always have to be careful which one they are actually talking about. So, but with big Witt vectors, everybody agrees that this is the multiplicative unit. So, yeah. So now I will take the Theis-Müller of -1, and so d log of that, so d divided by it, is a particular element in the Kähler differential. It's a 2-torsion class because -1 was a square root of 1, and d of 1 is 0. And this is an algebraic manifestation of the Hopf class in stable homotopy theory. And so now I will define the Rham complex to be the quotient of the tensor algebra of the differentials modulo the graded ideal generated by elements of the form dA tensor dA minus this 2-torsion class. So the usual definition is to say that dA tensor dA is 0, but I don't do that. I say that it's equal to this instead. Up to 2 torsion is true, yeah. So if 2 is either nilpotent or invertible in the ring, it's the same. Let me explain briefly where that this is not crazy. So if A is the Theis-Müller element of a unit, then if I take this relation and divide by A squared, I get this relation d log Theis-Müller u tensor d log Theis-Müller u is d log -1 Theis-Müller -1 tensor d log Theis-Müller u. And this corresponds to this relation, this well-known relation in Milnor K-theory that the symbol UU is equal to the symbol -1U. So this relation here is similar to that. Okay. So this Rham complex, as usual, is an anti-commutative graded ring, and it has a unique graded derivation that extends the derivation into the Kähler differentials and satisfies this. So it's not a differential. So dd is not 0, but dd is equal to d times this 2-torsion class. And the Frobenius map extends. So if we have an element A0 dA1 ... dAq and apply the Witt vector Frobenius to A0 and this divided Frobenius to the dAs, then this is a well-defined graded ring homomorphism. And it satisfies this divided rule, which is a manifestation of this epicyclic category. Yeah. So, but now you will remember the Verschiebung map on the TR groups. There's also a similar Verschiebung on or this transfer map on the TR groups. There's a similar transfer map on the Witt vectors. So it takes a Witt vector and just throws in a lot of zeros. So here xm is equal to am divided by n if n divides m, and otherwise it's 0. So we just take this sequence of elements and put in a lot of zeros. It's an additive map. It's not multiplicative, and and it satisfies these rules. It satisfies a projection formula with the Frobenius. It's an action of the of n cross through additive maps, and going up with Fn and down, going with Vn, and then Fn is n times the identity, and if m and n are relatively prime, Fm and Vn commutes. So, but this map does not extend to the de Rham complex. And so this is really what the big de Rham-Witt complex is. It's the largest quotient on which it does extend. And it extends in such a way that these four properties continue to hold, and then this formula here also holds. If you go up by the nth Verschiebung, use D, and down by the nth Frobenius, you get D up to this two-torsion correction here. Yeah, so that's the big de Rham-Witt complex. Yeah. Yeah. That's right. That's right. So let me go back to this diagram here. If K is a field, then we have the trace map from K theory to TR, and we have these maps from the universal algebraic structures back to the right-hand side. And now the map on this side is given as follows. It takes a symbol. So here A1 up to AQ are now units in the field. And you take their Teichmüller representatives and the D logs and multiply them together. So that's what that the map looks like on this side. Yeah, yeah. So maybe I should also say here that this top map from Milnor K theory to K theory, we now have an identification of this with the edge homomorphism in the motivic spectral sequence from motivic cohomology to K theory. And it has been a long dream of mine to have a similar spectral sequence converging to the TR groups, so that this lower map is the edge homomorphism of that spectral sequence. And maybe Matthew Morrow is is getting closer to realizing this dream. What? Yeah, I'm convinced it's true. So everything we have many calculations, and they all support this fact. For example, one thing is that as Con mentioned, if K is let's say if K is a field of characteristic P, then the top map is an isomorphism from the Milnor K theory mod some power of P to the Quillen K theory with mod P to that power coefficients. This is a theorem of Geiser and Levin. And so Con mentioned a theorem of myself which says the same for the lower map. And yeah. Okay. So what is the big de Rham-Witt complex? As you said, it's a quotient of the de Rham complex, and it's a quotient by a differential graded ideal. Well, I know it inductively. So yeah. So the way you construct this is to do it at finite levels and then induct up on the length. But it's not so deep. In the case of the integers, I know explicitly what it is. So, but if we follow Borger's philosophy, then we should interpret the de Rham complex of the big Witt ring as the differentials of A relative to F1. And then having a quotient of this modulo a differential graded ideal would correspond to having, oh, this was the wrong button, sorry, would correspond to having differentials along the leaves of a foliation, namely this quotient map defines a foliation. So we can think of the big de Rham Witt complex as defining a foliation on spec A as an object in this deeper world. Yeah. So I think that's what I had to say.
So that means that if I take an isotropic variety and if I take a case of good reduction,
yeah.
then I can get the corresponding local factor.
Well, yes, you can get that from the fiber of that variety at that point, but you would like to express it in terms. Yeah. Yeah. Yeah.
And then probably the fact that there is probably difference.
Well, there's that, and there's also the thing that if you have a finite field, then the p-typical Witt ring embeds into the complex numbers.
Yeah, exactly.
But the Witt vectors of the integers does not embed into them.
Sure. But this may benefit in the search of the other thing, because if you want to say the Witt vectors in the complex number, the way of thinking which is very different from eclipse, in the sense that it never actually constructs.
Yeah.
However, in that construction, there is something which can be constructed, the power limit. And what we would like to do is actually be able to get the local factor only using the power limit. That's really what we are after.
Yeah.
Because we know that the least will actually, that will depend on the choice of the power limit. There is no way to avoid that. But so what we are looking for some way of getting the local factor that doesn't use the embedding of the Witt vector into the complex number, because this doesn't really exist. But that uses the power limit. And for that, we would like to use the data and not go into something which is too abstract before.
Yeah.
In passing from the Rham complex to the Rham Witt complex, you gain on the left side of the square, you gain differentiable analysis matrix, something that differentiable wouldn't give while on the right side.
Yeah, it did not exist on the right. Yeah. Yeah.
So the contribution is at least of two levels. One to fix up the full differentiable, and second, of course, to get when you pass the isomotic group to get the isomotic group because the filtration the Rham Witt complex is isomorphic with situation with isomotic group you see on the right.
Yeah.
So is there more, I mean, the basic question I have is that is there more justification behind the introduction of the Rham, so the filtration, I would say, the filtration over the Rham complex? You see in
Are you asking about sort of the eidetic filtration of that kernel?
on the right you have the Rham complex without yet the
Yeah. Yeah.
So once you get over the WN, the weight filtration, then you gain already an additive property of the machine.
I don't think I know the weight filtration you were talking about.
Yes, yes. So I was wondering if
Uh-huh.
there is more things in the story that we taken moving from the right part of your diagram to the left part of this block. So which means moving from
Yeah.
linear picture if you want to see the story in a way.
Well, I think the situation is similar to what it was with Milnor K-theory, that when Milnor K-theory was introduced, it was not so clear that that was anything reasonable at all. And so Cato's higher local class field theory, I really think was the first thing that showed that this was really an important theory. And then later came this motivic cohomology interpretation. And so I would like to have the same thing on for the Rham Witt, but yeah. I mean, it's not. It's just that it's. I mean, what is a foliation on a manifold? It's just. Yeah. 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 Yeah.
What about the ability? Where is the ability?
Isn't that just that it's a differential graded ideal? Yeah. Yeah. That what? That.
Yeah, the dual formulation of ability when you talk about the form.
Yeah. Well, see, I think the easiest thing is to say if you have a space with a circle action, then if you look at the homology of X, then that becomes a module over the Pontryagin ring given by the homology of the circle. And what does this look like? This is an exterior algebra on the fundamental class.
That's exactly what you are.
So multiplication by the fundamental class gives you a differential. Why is it a differential? Because there's nothing in degree 2 here. But now if you're in homotopy instead, so if instead you look at stable homotopy groups, then this is not just that. And there is the Hopf class, and that the Hopf class gets involved, and that's the reason for this. Yeah, yeah. Well, see, so in the paper where Dulin and Ilussi introduced the Rham Witt complex for FP algebras, they did not notice this thing, that the Frobenius exists on the de Rham complex. So they first defined a de Rham Witt complex without a Frobenius, and then they calculated it for polynomial algebras in order to define it. And that you could not carry through for any commutative ring because some maps are not surjective. And yeah, so it's this miracle that that's the divided Frobenius already exists under the Rham complex that makes it possible.
The book are not that.
No, yeah. No, but I mean, it came from this question out of Borger's. So just asking what are derivations in lambda rings. Let's see, how is it they do it? No. Yeah. So for example, what you were talking about yesterday was the relative to z. So where the differential in the Rham Witt complex is w of z linear. So for example, there this class d log -1 disappears because -1 bracket -1 is in the Witt vectors of z. Well, this was, I mean, Sink did this because of his theory of p-divisible groups.